What's going on, AP Calc students? Mr. Ford here with another homework tutorial. This is 5.5.1. We're going to be doing problems 154 through 161, but we're going to be skipping 157. Whoops, I should just have written, I wrote this wrong here. We're going to skip 157, we're going to skip 158's part B and C, and we're going to skip 159. So we're going to skip a good amount of this. But there is still quite a bit to do. And the things that we are going to do are very important, and you're getting better at them every time you do them, and that's a fact that I really want everybody to recognize as you're working on this. So let's keep going. 154, without a graphing calculator, we're going to find the maximum, minimum, and minimum values for the function p of x, which is x squared minus 4 squared, over the interval from 1 to 5. And we are not allowed to use a calculator for this problem, so we won't be using one. Get out of here, calculator cam. It's already pretty small. Let's go ahead and do some work off to the side here. We're going to need to think about this. Our original function is, of course, x squared minus 4 to the second power. And if we're looking for maximum and minimum values on the range from -1 to 5, that is a -1. -1 to 5. So what we're going to do here, the process is pretty simple. We're going to take the derivative, we're going to set it equal to 0, and we're going to find any potential critical values of this function. So let's look for that first. Let's find the derivative, p prime of x. You know, the more I look at this thing, it might be better, before we take the derivative, to actually expand out this polynomial so we have a nice, easy thing to work with. This would be x to the 4th minus 8x squared plus 8, or plus 16, sorry, if we were to expand it, and that is just x squared minus 4 times x squared minus 4. So that's the original function still. So when we move into derivative world, p prime of x, we're going to have 4x to the 3rd minus 16x, and that will be it, like that. So the first question we want to ask ourselves is, when does this equal 0? And that will help to identify critical values of this function, potential places where the maximum minimum could happen. So in this case, let's factor this. Let's factor a 4x out of this thing, leaving x squared minus 4 in parentheses there. And this already allows us to pick out a 1, 0 at x equals 0. That's going to be one of our critical values. In other words, if x was 0, the derivative would be 0. So that's one of them. The other one's going to come from x squared minus 4, which can be factored into x plus 2 and x minus 2. That's a difference of squares there, kind of jumping out of this. So we have two other zeros at x equals -2 and x equals positive 2. So these are the places where our derivative equals 0. That's the first stage of this game. The next stage is to test all of these and see which one actually gives us the maximum and which one actually gives us the minimum. Now, we are going to ignore x equals -2 because it is not on the range from -1 to 5. So that means we need to test a bunch of things. We're going to make a little testing table here. This is called a candidates test. I'll write that down. Candidates. I always never know how the word candidates is spelled. Now, we need to test. We need to test any one of the critical values, so 0 and 2. We also need to test the endpoints because, as we've seen, on a given fixed boundary, say from -1 to 5, there will be on that range an absolute minimum and absolute maximum, but it might not happen at the critical values. It might actually be on the endpoints. So we need to test those too, -1 and 5. We're going to test all 4 of these. One of them will be the highest, one of them will be the lowest. And so we're going to plug them into our original function, which in this case is x squared minus 4 squared. And this usually, you can do these in your head maybe. This is no calculator, so we're going to have to crunch some numbers. This first one would be 0 minus 4, which is -4, and that squared is 16. Here we would have 2 squared. 2 squared minus 4 is 2 squared is 4. 4 minus 4 is 0, so this is 0 already. Not winning against 0. If you plug in -1, we get positive 1. 1 minus 4 is -3, and -3 squared is 9, so it's not that one. And if you plug in 5, 5 squared is 25. 25 minus 4 is 21 squared, and I'm just going to put 21 squared in here. I do not know what that is, but that's a huge number. I do know that this is going to be the maximum. That's the biggest number that we see. And this is going to be the minimum. That's the smallest number we see. And that's how you answer this question. Once you've identified your critical values, you then have to test them along with the endpoints in a kind of a candidates test like this and figure out which one's the absolute minimum, which one's the absolute maximum. So I would say that 2, 0 is the max. And 5, and then whatever 21 squared is, that's the max. 2, 0 is the minimum. And there you go. Pretty cool. Okay, let's move on into 155. We have another function, 5x to the fourth minus 3x squared. We're looking for the equation of the line tangent to y equals f of x at x equals 1. We're going to do this again later on in 158a. So this is a process we saw on the homework last time too. This is a problem you see on a lot of our questions. It's really, really popular AP Calc style question too. So basically the process goes like this. We know that the point is going to start with 1. We need to figure out what the point is. And that point is going to be 1 and then whatever the f of 1 is. And then we also need to figure out the slope. In other words, f prime of 1. So we need some information first of all. First of all, we need f of 1, which in this problem is going to be 5 minus 3, which is 2. So we know that this the point 1, 2 belongs on this graph. F of 1 equals 2. We also need the derivative. So f prime of x would be 20x to the third minus 6x. And once again, don't let that scare you. We just need f prime of 1, which is relatively easy to get. 20 minus 6, which is 14. So now that we know what the point the point that's going to be on the line and we know what its slope is, we can use this information to write the equation for the line using good old point-slope form from Algebra 1, which looks like this. Y minus 2 equals the slope of 14 times x minus 1. Now, this is the answer to part A. That answer will work just fine. Now, we could go further and make that into y equals form, but we don't need to do any of that. So, actually, no, it might help because I think in part B, we have to use our tangent line to approximate what f of 1.1 would be. So maybe we should just take this right now and move it into slope-intercept form. Y minus 2 is equal to 14x minus 14. So y is going to equal 14x minus 12. Like that. Just moving some numbers around. Now we need to know, this is for part B. We're going to use this information here to figure out what part B is. The idea is that plugging 1.1 in for x in the original function would be really hard to do. But plugging 1.1 into this function is actually really simple to do. Actually, you know what? I withdraw. What's even easier is to use the original form. Here, I'll show you. Y minus 2 equals 14 times 1.1 minus 1. The advantage here is 1.1 minus 1 is 0.1. And this is pretty easy to figure out. Y minus 2 is now equal to 14 times 0.1. The next step there, sorry, I'm kind of all over the place, I guess. Y minus 2 is equal to 1.4. And if you add the 2 over, you get 3.4. That is the approximate answer for what we think this function is doing at that time. So again, the idea here is that actually plugging in 1.1 into this function is really hard to do without a calculator. But without a calculator, we can easily use the straight line that we've got, which is a reasonable approximation of the function within a certain accepted range. As far as whether this is an overestimate or an underestimate in question C, that's going to come down to f double prime. Because f double prime will tell us the concavity. F double prime of x in this problem is, I'm just looking at the f prime we have over here in this section, it's going to be 60x squared minus 6. And we're concerned about the concavity at 1.1. So f double prime of 1.1. And we don't really need to actually calculate the answer here. We just need to tell if it's going to be positive or negative. And it's pretty obvious. If you plug a 1.1 in for x right there, you are going to get a positive number because it's going to get multiplied by 60 and then subtract 6. So it's going to be positive, which means it's concave up. Now let's draw a picture for a minute really quick. I don't know what the function looks like, but I do have a function that is concave up. Looks kind of like this. Concave up like that, maybe. Concave up. And I also know that the derivative, f prime of 1, is also positive. So I know it's concave up and increasing. So let me figure that out too. Concave up and increasing. Kind of like this. So again, zooming in on this graph, we know that this graph is concave up and increasing. And if we were to draw a line, let's pick a point on this and just draw a tangent line on this, you can pretty clearly see that the tangent line is always going to be underneath the function, like that. So it's because it's concave up that the straight line will always be an underestimate. It's always going to be below the function, so it's going to be an underestimate, like that. Okay, those are two pretty heady problems to start off with. A lot of review on there. Let's go into some derivative examples in 156. These ones, again, we might need some space for, so I might move off to the side and do a lot of work a little bit. Just kind of a cursory look at these things. Question A is going to be a product rule problem. Question B, I'm going to immediately rewrite that as the cosecant of x. That's just 1 over sine. Question C, this third power, normally I would expand this all the way out, but this third power there is really freaking me out. So we're just going to use the product rule. It'll actually be faster to use the product rule there. And this will require a chain rule. That part of it will require a chain. And question D will also be a chain rule problem. So just kind of like previewing in my head what we got to do before we even start the problems off. So I'm going to move off to the side a little bit and get some room for these. For question A, we got f of x equals x squared tangent of x. So let's go ahead and practice the product rule really quick. We have a thing times a thing, x squared times tangent of x. So in order for us to take the derivative here, we're going to need to remember the product rule. The original first thing times the derivative of the second thing. And of course, the derivative of tangent is secant squared. Plus the original second thing, tangent of x, times the derivative of the first thing, 2x, like that. Now, of course, we usually clean these up a little bit. Usually you see a polynomial thing in front and the trigonometric thing in back when you have trig involved. So I suspect a formalized AP Calc question would probably look like that as the final answer. Or the order might be different. There's just things that can be there. So, question B. We have the cosecant of x. We'll just answer this one right now, right here on this page, because it's very simple. This is just, you should memorize the derivative of cosecant, which is going to be negative cosecant cotangent. Like that. The sooner you can memorize those trig derivatives, the better. They're just off your table for a little bit. Question B. We are going to require the product rule for this problem, although, you could make the argument that expanding it would be faster and working as a polynomial, but I don't think so because of that third power there. So again, our original problem is 2x plus 1 times 3x minus 1 to the third power. Now, since this problem also requires the product rule, we're going to do it over here, but it also has a chain rule inside of it. This second part of it, the g of x, if you want to call it that, in your product rule, that's going to require the chain rule. So this one might be one that's worth setting up. I'm going to use u and v in this problem just for the sake of variety. This is the way I was taught when I was in high school myself. Oh, I'm writing over my own face there. Here's the two things being multiplied together. You could write f of x and g of x. I'm just using u and v for fun here. The derivative of u, or du, would just be the number 2. But it's the derivative of v that's going to give us a few problems. dv. Well, first of all, we got to do chain rule. The outside part of this chain rule is going to be the third power, which we will bring down and then decrease the degree right there. So there's the derivative of the outside part, but now we also need to multiply by the derivative of the inside part, which in this case, again, is just 3. Derivative of 3x minus 1 is just 3. So if you put it all together, the 3 times the 3 becomes the 9. We have 9 times 3x minus 1 to the second power. And that's what we'll use for dv in this case. And I like to put a little cross in here to help separate the different chunks. So going back over to the drawing board, when it comes time to take the actual derivative, f prime of x, we are going to do, first of all, we'll do u times dv, or original first times derivative of second. That would be 2x plus 1 times 9 times 3x minus 1 squared. We'll clean that up in a little bit. plus, now we'll do v times du. So we'll just do 2 times 3x minus 1 to the third power, like that. And we'll go ahead and clean this up a little bit. It will be 9 in front. And then the order does not matter for any of this other stuff here because we're just multiplying it all together. So I suspect if I was to look up the answer in the textbook, this would probably be what it would say, something like that, which is exactly what it says. Hey, cool. Neat. Don't let those chain rule problems freak you out. You get a little better at them. The more you practice them, the more you start to see the chains happening inside. And you got question D. Here's another chain rule problem, but we have enough space to work with it right now. Let's start with the outside part, g prime of x. Well, the outside chunk is the cosine. So this is actually a triple chain rule if you look at it the right way, but we'll deal with that in a minute. The outside part is cosine. The derivative of cosine is negative sine. So we'll start with the derivative of the outside. Negative sine of the original inside, not touching it at all. Now, of course, since the inside is its own function, has its own stuff going on, we need to multiply by its derivative. Now, this is also a chain rule, but it's an easy chain rule because x plus 1, the derivative of that is just 1, so we don't really need to worry about that second chain rule happening. However, we do need to worry about the square root of something. The derivative of the square root of x is 1 over 2 times the square root of x plus 1, like that. That is as far as you need to go for this problem. You can leave it like that if you want to, although, since we have two things multiplied together and there's a fraction with a 1 on top, it's kind of like an empty apartment that just needs a roommate. So let's put the top part on top, and we'll put 2 over the square root of x plus 1 in the bottom, and there we go. We'll call that a day. And I know those square root of x plus 1s look like they can cancel out, but they cannot, because one of them is inside of a sine function. Weird. There you go. We will not be doing 157 because it's ridiculous. We will do 158 because it's just another rep of writing the tangent line of a problem, so let's just get to it. It won't take us very long. It might be helpful just to remind yourself what point-slope form is. We kind of take for granted as AP Calc teachers that you remember this from your Algebra 1 days like that. Although it gets kind of a glow-up in AP. It becomes y minus f of a equals f prime of a times x minus a, like that. Now, in this case, they did actually give us both the x and the y, the 1 and the 0. So we will be plugging in, we'll be plugging a 1 in for a and a 0 in for f of a, which is cool. The only thing we don't know is f prime of a. So f prime of 1 essentially is what we need to find. F prime of x in this problem is way easier than it was before. 4x to the third minus 3x squared. And then f prime of 1, in this case, again, we're borrowing the 1 from the given function we have right there. This is just going to be 4 minus 3, which is 1. So we'll plug a 1 in right there. And so the equation will look like this. It'll be y equals 1 times x minus 1, or just y equals x minus 1. Simple. We do not need to worry about the rest of that problem. It's too easy for us. Okay, let's move on. Actually, we don't need to worry about it because normal lines are no longer on the AP Calc test. So you don't need to worry about it. It's the same game, but it's the slope's perpendicular, so you got to do that -1 over reciprocal thing. We will not be doing 169 either, or 159. It's not a terrible problem, but it is just weird it's weird for weirdness sake, and I don't enjoy problems like this, so we'll skip it. 160, we have Bob's cat Alice. He's doing wind sprints up and down the hallway of his apartment. Suppose that t minutes into her wind sprints, Alice's velocity in feet per minute, good thing to point out, is given by the formula v of t equals that thing, 12 sine pi of t, So, first question is, what is Alice's acceleration at t equals 6 minutes? Right away, I can tell you just it doesn't say this in this problem, but based on the ridiculousness of this function here, this is a calculator question. At no point are we ever going to be expected to take that derivative. It's not actually too terrible to do, but it's way too mind-consuming. This would be a calculator question, so we'll get calculator cam ready to go. Hello. We're back and we're on focus. Okay, so first thing we got to know is what's her acceleration. Alice's acceleration at t equals 6 minutes. Well, the thing we got to know for this problem, for a, is that a of t is v prime of t. So we are going to take the velocity function, we're going to take its derivative, and we're going to plug in a. Now again, this is not a horrible derivative to take. We can do it by hand. I will do it by hand just for funsies. V of t is 12 sine of pi over 4t, like that. The derivative would look like this, a of t. It would be 12 cosine of pi over 4t times pi over 4. So, it's not too terrible, but we'll do the calculator for most of this. 12 divided by 4 would become 3, so it'd be a 3 pi cosine of pi t over 4. And actually, it's not so horrible, but let's let the calculator do it. We are going to start by going into the y equals menu and programming in the original velocity function. We're going to need this in the calculator in a moment anyway for the rest of it. So we want pi x over 4 inside of that parentheses. Very careful to plug that in and make it look exactly correct. The next thing we need to do is we need to go out to the main screen, push alpha F2, and pull up our derivative formula right there. We'll do the derivative with respect to x. Here's in this box, you could just type that in again. It's not too tough to do. 12 sine of 4, pi x over 4, like that. Or you could go into the calculator, open up the F4 menu, and select y1, since we did that anyway. And then finally, we are going to make this when x equals 6, because we really want to know what the acceleration is at 6. And it looks like it is 0, which is an interesting answer, but I guess that makes sense. If I were to plug in 6, I would get 6 pi over 4, which is the same thing as 3 pi over 2, which is 0. So yeah, it is 0. That's fine. So the first answer to this question, what's the acceleration? I guess if I'm looking at this right here, a of 6 equals 0. And we also should put units on this thing too, since it was given to us. Feet per minute squared would be the final thing there. Let's get calculator cam out of the way a little bit. Let's talk about question B. What is Alice's displacement between t equals 4 and t equals 24? A wonderful word we have not talked about in some time. Displacement is just going to be the integral from 4 to 24. Displacement tells us the change in distance. When you move from point A to point B, if you subtract point B from point A, it tells you how much your distance has changed. That's called displacement. We'll compare that to total distance in part C, but we'll deal with this all on the calculator, in fact. For part B, all we're going to do is the exact same thing, but we're going to run it through an integral instead of a derivative. In this case, we're going from 4 to 24. And displacement would be the integral of velocity, which takes you back up to position. So you have velocity in the middle, up goes to position, and down would go to acceleration. So this time we're running this thing, 12 sine of pi over 4 times t dt. We're going to let the calculator handle this calculation right now, and we'll show you how to do that in a couple different ways. Again, let's see. Let's bring this up. If you open up alpha F2, you can find your integral function right there. Bam. Pop that up, and we'll put 4 and 24 in this little box. Now, you could, again, type in the function right here, but we already programmed it into y1, so I'm going to use that. Alpha F4, I'm just going to select y1 from that list. And we're just going to put dx in here, since the original function is in terms of x, and this will just tell us the displacement. It's going to take a minute to think about it, and it's going to spit out an answer. And that answer should be like negative 30 point something. Yeah, negative 30.558 or so. And of course, we need a unit on this. Since we had feet per second for velocity, going up to distance, this is going to be feet, like that. Now, that is not the total distance traveled. That's the change in distance that happened. So, for the total distance traveled, what's going on here is that we are... what we need to do, I'm trying to think of a way we could take the antiderivative of this thing by hand. I don't want to do that. No, for the total displacement, a total distance, we need to remember that some distance is positive and some distance is negative. Obviously, there's been some negative distance because the total change was negative, but we need to make sure we can account for that. So what we're going to do is we're going to do the exact same integral, but the difference is we're going to put that entire inside of an absolute value. We're going to kind of force this to be positive, even if it's not positive, because we don't really care about where it's negative. We care about what distance was traveled, whether it was moving to the left or to the right. Doesn't really matter. Now, if you're handy with a calculator, you can actually arrow up twice and grab this exact same input. then you can kind of go over here, and you can put an absolute value in there. Absolute value lives in a lot of places on the calculator. Inside the math menu over in number is where I kind of go for it. I'm going to go ahead and put y1 in there again. I want to say it's an alpha f1. Nope, alpha f2. Alpha f2 right there, first option. Cool. So what this will do is it kind of forces the inside of the derivative to be positive, and so it will give us a total distance traveled answer. It should be like 45 something, I think. It's got to think about it, though, for a minute. She's still thinking. You can see the arrows. You can see the wheel turning right there. Ooh, I didn't realize we had asked so much of our calculator today. You know, what's interesting is the textbook actually has exact answers here, which makes me believe we could have done this by hand. That's, in my mind, lunacy. Oh, that's not what the book has at all. Ooh. Oh, you know what I did wrong? I didn't do anything wrong. I just didn't change the bounds. It's from 2 to 8. That's correct. That integral is correct. We got to go down here and change it from 2 to 8. So I'm going to go ahead and push enter on this. Jeez, you guys probably watch these videos sometimes. You're probably at home going like, what are you doing, Ford? I'm going to let that run while we start looking at the next question. And as the answer pops up, we'll go back and add it. So the next question is also going to require a calculator, I think, but I haven't looked at it too closely here. Examine the equation x of 1 plus the integral from 1 to 7 of v of t dt equals 22. Oh, look, the answer popped up. Sorry, I'm going to interrupt myself. Looks like the answer is 45 something, like I thought it would be. 45.837. And again, that would be in feet because we're actually talking about the total distance there. This is not from 4 to 24, man. It's from 2 to 8. Integral from 2 to 8. Pretty cool. Okay, let's move on to 161. Examine the equation x of 1 plus the integral from 1 to 7 v of t dt equals 22, where v represents the velocity of a particle moving along the x-axis on a sheet of centimeter grid paper in centimeters per second. Wow. See, it's either a bug walking on a tightrope or it's a particle on the x-axis. Pick your problem you want to do. At t equals 1, the particle is at the point 7, 0. Okay. So we kind of have an initial position. We know that when this thing starts at t equals 1, the particle is already at 7, 0. So in question A, we're going to write a complete description about what the integral from 1 to 7 is computing. Use correct units and be sure to mention the meaning of the bounds in your description. So the integral part is just the change. It's not where it started. It's just how it's changing. So for question A, we have to say something about this. This is that integral, the integral from 1 to 7 of v of t. This is the integral of velocity. This is going to represent the change in position from t equals 1 to t equals 7. And change in position, you could use the word displacement there instead. That is what displacement means. Another way to think about displacement, which is a cool to think about, because this can be used for I shouldn't talk and write at the same time. Because this can be used for all sorts of other situations besides velocity and position. It might be good to think about this as accumulated velocity. In other words, if you add up all the speedometer readings over a very small amount of time, you end up getting the actual distance being traveled. That's a good way to think about it there. Let's see. Question B, though. In the context of the problem, what does the value 22 mean? So 22, let's see. I got to think about this. X of 1 plus that. So 22 represents, if you think about this sentence here, this is where it started. And this is how it changed. And so 22 is kind of where it ended up. That's where you want to think about this. It started at, we know it started at 7, and then it changed by some amount, and then it landed at 22. So 22 is where the particle is, the location of the particle at t equals 7. That's going to be your answer for part B. 22 is the location of the particle at t equals 7. That's it. That's where it actually is. Now, as far as question C goes, that's actually incredibly easy to evaluate. You might be looking at this problem and go, how could I possibly know that? But think about it like an algebra problem. We know the initial position is 7. We know there's an integral thing happening in there. But then the particle ends up at 22. So it has to travel by 15. 22 minus 17 basically is what's going on there for question C. 22 minus 7, sorry, is 15. And centimeters is the unit, because this is talking about centimeters per second. Whew. You know, I didn't intend that for it to be so long, but, you know, that's kind of nice that these, I do take my time explaining these. I don't just rush through them. So I think it's really helpful to have these videos. And there you go. Hope you guys have a great time with this one. I'll see you in class. Namaste.